start your presentation.
Hi, I'm Scott Kennedy with Cornerstone Architecture, and I was asked to present a building today, which is called the Heights. So this is, at the time, Canada's largest passive house buildings. I'm going to assume everybody knows what a passive house is, but a passive house basically is an energy target. It's somewhere in the step 4 to step 5. In fact, it's a little higher than step 4 or step 5 in our current step code. And it's really a targeted energy consumption. It's not a better than, it's a target that you have to hit. So this is the first really large building we did. It's called the Heights. It became a fairly important building in that the mayor came to the opening of the building because it was considered kind of a groundbreaking set of ideas at the time. It's based on an idea that was really started in Saskatchewan in the 1970s and really got really taken over by the Passive House Institute. And so that is kind of where this comes from. So this is the project, and this is the presentation of what we're talking about. So there's the building finished. It's on Hastings Street, about 2 blocks east of the Peony. So these are the specifications for the building, which are very high specifications for the Vancouver climate. And these are the important parts of a passive house. It's very highly insulated. It's the detailing to eliminate thermal bridging. We have very, very high efficiency heat recovery, and we have a very airtight envelope. These are basically what your plans are. So we did an energy model for this project based on a program called Design PH, which is a program developed by the Passive House Institute, and it feeds into a giant Excel spreadsheet, which is called the PHPP. So this model is done to help us enter the data and all the windows and everything else. And at the bottom, down at the bottom here, I think you can see there's that's the elevator as it goes down into the parkade. And those are all very difficult things to figure out how to deal with in terms of thermal bridging and other kind of modeling. So what happens in a PHPP is you get this balanced equation for your energy. And so you have all the losses on the left, and you have all the basic gains in the building on the right. And the red is what you put in with actually put in with your heating system. Now, typically in these multifamily buildings, that's actually, you should be able to get that below 15. This is at 7, which is, or 8 or so, which is really amazing, to tell you the truth. And it's because it was our first building, we probably over insulated this building, and we relied too much on solar heat gain. So that's the 2 takeaways from what we did on our very first attempt on the building. But you can see that the windows are the biggest loss, and the ventilation is also a significant loss. We had detailed the building quite well, so thermal bridging wasn't a big deal. And then the walls and the roofs and other elements that were in there. So just some envelope details. We looked at the idea of insulating on the exterior. We looked at the idea of insulating on the interior. And we also looked at whether we would do the concrete floors at the base above or below. And we've concluded in the, in many ways, I think as we move along, I think exterior insulated with Roxel is the very best way. And certainly for using concrete floors, I think a combination of above and below is the very best way to deal with thermal bridging. So these were the wall options we looked at. Exterior insulated, various options. We ended up doing interior insulated, and that was for a bunch of reasons, but it was also the choice of the contractor at the time. And you can see we try to be very careful in where the air barrier and how it's going to work around windows and all those kinds of elements. And so there are advantages and there are disadvantages to each time for each type of system that one might use. And I think things are changing. Embodied carbon is becoming an important piece, and other issues become more and more important as we move through a changing world that we're working on. So we looked at all these different options, and we came up with advantages and disadvantages of each one. And anyways, we ended up with this one, which was an interior insulated building. We've done 4 or 5 buildings this way now. There are advantages and there are disadvantages to every single way one would do a building like this. We actually built some models of this to help us understand how it would work and help the trades understand how we were going to put this building together. You can see this one is actually insulated on top of the concrete slab. So we did that because it really is helpful for thermal bridging. And so this is how we did this particular building. So here's how we built the walls. You'll see that that interior wall is kept back from the exterior wall, which is one most unusual little detail. We then lapped our air barrier material up the walls as we built the building, installed the windows. We then insulated the outer cavity. We then installed, it's an EPS foam with a film on it, and we tape sealed all that. That's an expensive tape we use too. It's a acrylic seal type adhesive on the tape. It's designed to last 100 years. Once you put that on, you'll not get it off, but it's expensive, 69, 70 cents a foot. We then furred in a service cavity wall on the inside of that. That's so that you don't pierce your air barrier with any of the plugs and all the other services that one would put in. And then we finally insulated the project. So as part of what we wanted to make sure that that wall was going to be okay, particularly on that outside of the plywood, we did have that, all of our leaky condo syndrome. So we actually ran a little WOFE analysis. Our building envelope consultants actually ran that, but they felt that the moisture content, it varies through the season, but it always stayed well within what we were hoping to do. So there's the building under construction, and you can see that blue lapping at the floor lines. That's those air barrier that was wrapped around. And that does present some construction challenges, but the contractors were able to stay on top of it. We did have them trained at the BCIT High Performance Lab in how to build a building like this and what's important about these various properties. You know, here's that service cavity wall showing all the various services that go in there. But again, we've got this continuous air barrier taped behind it. And then there are some beautiful things that happened. There are some special details we came up with for how we could put sprinklers in and eliminate drops, and a lot of air sealing things that one has to do when one does a project like this. And that's the main floor. And you'll also see that, again, to deal with thermal bridging, we had a concrete column that goes through the floor and comes up into the building. We actually decided to over insulate them on top. Again, I think we overdid it in this building. I don't think you need to be quite as aggressive, but again, this is our first building of this type that we'd ever done. So that's kind of how we ended up there. And then we made some decisions about how to install a window. We did it outboard. We set the face of the window flush to the siding. We did that for a bunch of reasons. But the biggest one was it just was simpler to do, less tie-ins for the contractor to do. It's not necessarily the very best place to put it from a thermal viewpoint. At those windows, what you really want is those lines to be quite straight, those therm lines. And you can see that they bend quite a bit because we're outboard with that window. But there are practical reasons we wanted to do that. And one of the reasons was you see that big step on the inside of those windows. Sometimes those go out to balconies, and it became a step to go out to the balconies, which was quite useful. And then there's lots of thermal bridging issues that one has to deal with, and particularly at the ground floor, where you've got these concrete slabs that go inside to outside. And how do you stop the thermal movement? One of the beautiful products out there are these Isocorp system, which actually provides a structural thermal break in a slab. Really difficult to get engineers to spec that here, but this is a picture of the one I saw. I think it was in Germany. I took this picture where you can see it's freezing on the outside and it's warm on the inside, and this does a marvelous job of a thermal break. But they're not common here. We are starting to see them. They're very expensive. So we had some thermal bridging problems ourselves where we didn't want to translate the cold steel up into that warm slab. Ultimately, that slab's warm in this building. And so what we did is we just use a wood block. It said, you know, that's a real simple, cheap way to do it. So again, this is our first time through it, and we were working out all of these various details and how we would make this easy for the builder to build, and we worked with the builder quite a bit to do it. This is a detail, again, where the outside wall, the inside wall meets the outside wall, leaving a bit of a space, trying to make sure that they could tape the air barriers, trying to make sure they could get their fingers in there to do all that work. And this is where we ended up, and certainly it worked. In the thermal modeling, we did a lot of thermal modeling of the joint junctions just to see how they worked. In this particular case, we have spray foam at the floor lines. That was to enable improve the thermal insulation. Also, it's a vapor impermeable layer. We were a little worried about condensation, maybe on that cold wood beam. I'm not sure if I'd worry about that today or not. Those are all things that we were worried about. There was obviously a problem at the slab. You'll see there's an interesting detail where we stepped the edge of the slab. It's quite a thick slab, but we stepped it. The reason we did that, there's those two 2x8 blocks that you see there. That's actually so that we could attach brick angles to the building, and so that we could actually attach handrails to the building and not have a thermal bridge. So that's kind of the thinking that we were doing as we tried to make that work out. Here's basically a typical detail at the exterior wall. We have a little bit of a concrete curb there because, you know, we don't want to have a waterproofing problem. We do a little bit of you'll see a little detail there in the corner. This is basically a water stop product that's in there to give us a secondary barrier, although we're bringing our waterproofing membrane up and into the sill, which is kind of a common practice here in BC. And then sometimes we had this similar detail, but maybe where the brick was, and we had some upstand walls. So again, all these details were fairly carefully considered as we went through the building. That would be an isocorp if you could do it. It turns out we couldn't in this particular building, but we ended up top insulating and bottom insulating the slab to deal with that detail. Again, we have shear walls going through the building, so we brought them up the top. You could bring them down the bottom into the parquet too, but we brought them up the top into the commercial space to deal with the thermal bridging. There's a typical detail at the deck, and I think this is kind of something that we'll talk a little bit about as we move along to some of other assemblies, but this little detail here, not wanting to get condensation on that plywood and having your waterproof membranes go in here, that's really your vapor layer. And how much insulation can you put below before you create condensation problem? We're actually finding we can fill it. As long as we put enough insulation on top, we can fill it, and we do have some data where we actually measured it on this building. I'll get to that a little later. Again, we had the beautiful thing about having the structure on the outside, it made it very easy to attach anything to the outside of the building. So we made judgment calls, and these are why we did it. You know, and there are other firms and other projects where we're making different decisions, but these are the decisions we made for this particular building. And you can see the sunshades going up. Now, these sunshades are not large enough. I can tell you that right now. And we also have a problem with urban heat island effect and climate data that's really outdated. It's not dealing with the future. And we are getting overheating in this building. But those are things we can talk a little bit about as we get to the end. These little slots you see here, that was our idea. This is down in the Park 8, down at the elevator lobby. And we needed to have a little bit of a structural connection, but we didn't need to have the whole slab go through. So what we did is we left slots. And in those slots, we stuffed mineral wool insulation with a fire stopping product in order to deal with the thermal bridging. So those are just some of the thinking we did. So it's not perfect, but it goes a long ways to helping your energy model. Now, anytime you're doing buildings now in BC, you're going to be having to do an air tightness test. This building turned out to be amazingly tight for its size and its complexity. And so the pass valve standard is 0.6 air changes an hour. This one hit 0.29. And basically, you could use a blower door that you would normally use on a single family house to do an 85 suite apartment building. So it's very tight. And again, it really relies on having, in my mind, trades that are educated and to what the objectives are, and to really be attention to the air barrier continuity details. And that's really, really important. And so, you know, I mean, a good test, the single family house in Vancouver is 3.5 air changes an hour, and they get them tightened up to maybe 1. So you can see that the standard, the pass valve standard, is very, very, very important. So there are other parts of a building that are important too, right? So the elevators are quite a high consumption building. We specified these new elevators. They're not hydraulic. They actually have motors that run with the car up and down. And at 6-story height, they'll actually put some regenerative braking back on these things. So in fact, they will start to generate energy back when they're trying to slow down. So these are all just interesting pieces. Now, this is a very controversial detail that we did. This is the inside of the elevator shaft as it goes into the parkade. So remember, you got a cold concrete wall in the parkade. We didn't really want to insulate on the outside because the cars are going to hit it. So we insulated on the inside. And what we did is we put these giant wood blocks in to attach the elevator rails to the building. And remember, it's a concrete shaft anyways, up above. It's a concrete elevator shaft. That's what we're doing these days. So this is how we did this detail. Now, from a building envelope point of view, the weird part of this thing is there's really no vapor control. And so if we had a lot of moisture, technically it might condense on the concrete behind this. But again, the rock wool is not going to deteriorate. So we were pretty confident that, and the parkade actually stays warmer than you think. So we're pretty confident it was going to work. So it hasn't proved to be an issue. So the way we ventilated the building at the time, we decided to go with these units, which are Zehnder Comfort 550. It's a highly efficient units, about 85% heat recovery efficiency. They're basically something you'd use in a house. But because they were small apartments, we put 5 apartments on these units at the same time. And what we did is you want those outside ducts to be as short as possible because they're basically bringing cold air into your building. And you basically had to insulate that duct. So we wanted to keep them short as possible. We put them on the roof. Good for the winter, good for the short ducts, bad for taking in fresh air in the summer that's overheated from the roof. The heat island, urban heat island, as we talked about. So there are issues that were good and bad about the way we did it. They work quite well, and they certainly provide great air quality in the building. But you know, what we did is see all these. This is the 6th floor. So you see, there's just a whole bunch of closets on the 6th floor that we put these units in, and we did that so they're very easy to service. So the manager can go in and service the filters quite easily. And then there are fire dampers at each floor level, but again, they're off the corridor, so they're easy to access. Again, it's a rental building. You might have to go in occasionally. So this is kind of how we did it. That's one of the units sitting in a closet with these ventilation ducts that go down through the building. Once we get into the suites, we distributed the air. Now, again, all that drywall is the fire stopping so that this is all below fire level. We distributed the air with a plastic pipe system. We're starting to see a little more flexible system than this in a couple of our buildings. The reason we did this is that we wanted very quiet air. You do not hear the ventilation in this building. And the reason for that is this silencer box that you see here pointed out there. That takes the noise that's coming into the suite and puts a silencer, and then it pipes this air very quietly. You do not know what's going on in the suite. And the other piece of that ventilation is each suite has a button in the bathroom and a button in the kitchen. And if you hit it, it'll actually increase the volume of air for the whole stack of 5 suites. So we're ventilating 5 suites at the same time with 1 unit. It was inexpensive. It gave reasonably good controls. And that was the reason we did it. I mean, again, this is our first shot at it. Just trying to get a client to even do it takes a bit of work, right? But we did get a client to do it. In fact, we're building a townhouse project with the same builder and the same clients right now. That's a passive house building. So the other piece that's really important in a multifamily is hot water. Hot water is a very, very large user of energy in a multifamily. And one of the keys is you're always circulating hot water around the building. And all that hot water line is radiating heat into your building. And I know you've probably been in the hallway of an old building that is totally overheated because the water lines are running through there and circulating hot water. So the key here is you want to increase the insulation on these hot water lines. You want to make sure that when you connect them, you're connecting them with a thermal bridge free as much as possible. There's always a few seismic braces that you can't do that with, but for the most part, you can hang them. And so you want to really detail them well. And this is that hot water line as it comes up to the manifold, up into the unit. From once the water's into the unit, we don't worry about it in the passive house. The other thing that we learned and this came up very late because there was a translation issue between what a what they call a downpipe and what turns out to be a vent. So this is the fact that plumbing vents coming through the building actually bring warm air, often bring cold air up into your building and up the pipes and out the roof, and they actually cool your building down. And so we found that out right at the last minute. So we had to run some insulation very quickly onto those plumbing vents. So that got taped on really at the end. We're now starting to use air admittance valves. So what we do is put a valve at the top. The city's allowing us to do this now on the very top of the stack outside. And what happens is it allows air in, but it doesn't allow air out. So we don't get that convection loss through the pipes. So the building actually has a hot water system using gas, but this is what we're doing now. So lessons learned and technology in the market. These are heat pumps, and they are use carbon dioxide as a refrigerant, which is really not a greenhouse gas in this kind of quantity. It has a global warming potential of 1, whereas most heat pump gases are 500 to 1500 or higher. So if it leaks, it's not a big deal. And it turns out these are very good at making hot water. And so in this building, I actually, a little later, I'll show you, I kind of figured out if I had to put this system in, what would happen to this building. These are very, very good units, and we're using a lot of them. I've got a bank of 18 of them going into a building right now. And for a building like the Heights, we probably use 6 or maybe 8 of them to heat a building like that. Now, in terms of appliances, we're using heat pump dryers. So we're no longer taking interior air, heating it up, taking some moisture out of your clothes, and then throwing it outside. We're actually recirculating the air. We're actually basically using a heat pump to take the moisture out of the clothes and put it down the drain. It's supposed to be easier on your clothes. It is slower to dry, and the technology is fairly new, very old in the European market, very new in the North American market. And the drying time is where we're stumbling the most with our clients on that. And the other thing that is important in a passive house is just that they want you to use those hood fans, but they got to be quiet or nobody uses them. So again, we use recirculating fans with charcoal filters, but then of course our heat recovery ventilator, it has a vent usually in the kitchen. So, and 24/7, we actually are taking the air out of the building. So we actually had a little bit of ability to do some energy or some monitoring on this building. So there were some instruments put in looking for durability and performance and condensation and some vertical movement ideas. And so this is some of the data we got. I haven't updated it. I haven't updated it for quite a while since I did this presentation, but this is kind of what we did. And so we actually measured the shrinkage of the building. We measured the effects on the roof decks of that plywood, whether that plywood was going to get any condensation on it. And we looked at the indoor temperatures. This was our problem with the building, right? We actually found that the building overheats. It uses very, very little heating energy, and it does overheat. And so we're working on another building about a block and a half from there that's under construction now. And on that one, we're actually putting exterior shading on the building on the south. And we are going to cool the supply air. So that fresh air as it comes in, we will be able to put a little bit of cooling in. And we think that'll be good. We've up to, until we get real massive climate change. Then that might not be enough, but we think it'll look after us for quite a while into the future. So, in the energy modeling we didn't see the overheating, and the building is actually a certified passive house, but in the reality, I think we did see one, and I think urban heat island effect, maybe not as good a shading as we should have done on the windows, definitely too high a solar heat gain on the glass. These are all mistakes we made, but live and learn, that's why we do these things. And so this is kind of what we found out, that we did see overheating in those particularly in the summer. And so these are, anyways, very things that we did. What we did find is that humidity control was pretty good in the building with the ventilation, the continuous ventilation. No real concerns with humidity control. The odd time we got the odd spike, but generally pretty good. And then those spikes tended to disappear right away. So the ventilation system is basically dealing with humidity quite well. And we looked at monitoring CO2 in the suites. And again, CO2, you want to keep it below 1,000. Is kind of the natural environments around 400 these days outside. So this is kind of a plot of kind of where we saw that number. So it, again, occasionally got up there a little bit, but that's probably somebody having a party or something else going on. But generally it was working quite well. Now this is that envelope performance with the relative humidity at that sheathing. Remember that sheathing's on the outside edge. And so generally, we were in a range that everybody was fairly comfortable with in terms of the actual moisture content on the sheathing. But it does occasionally get up there a little bit. And but again, it dries out. So there hasn't been any noticeable issues at this point in time. And once we got through the second winter, it was a lot better. So once it dried out, it actually improved quite a bit. So we got that point where we're pretty confident that there's a short period of time, it's a little bit high, but it tends to be better and better as we move through. Now this was interesting. This is the roof plywood. Now remember, we were worried about that roof plywood being quite because it's got insulation below and insulation above, and there's some potential. Again, there's good air barrier, so there's not a lot of moisture moving through the envelope. And we're finding that actually that plywood actually stayed well below where it should be for moisture content. And there were really no concerns once we got this thing done, that it was working quite well. And insulating on top is really the key. And remember, this gets open to the night sky. So this gets really, really cold temperatures at night. So these were kind of our conclusions from the analysis that we did, that really exterior insulation is the best way to go. Vertical movement is important in these buildings, but it was interesting that the exterior walls didn't move anywhere near as the interior walls. So they're not drying out as fast or something like that, or the plywood is stabilizing them. Not quite sure what that is. But this movement is quite important. We're doing a building right now with a bunch of exterior decks, and they're on posts. And so we know the building's going to shrink. The question is, how much shorter do we have to make the posts on every floor so that that balcony always slopes to drain and doesn't backslope into the building? And we're picking about 3/8 of an inch of floor. And again, it depends on the material and the moisture and when it's built. There's so many things that come up, but these are all important things. So the last piece is how does this thing work energy-wise? So this is the passive house standard. The allowable on the left is 15. Now remember, these numbers for a typical North American building are closer to 100 or 150 even, right? Like they're significantly higher. So this thing actually, funny enough, came out very, very close to the modeled energy. Now the reason for that, I think, is actually that we have more internal heat gains than it actually is happening with the building. And I say that because from this slide. So we seem to have a lot higher actual plug load energy than was modeled in, and we're not quite sure why, and we're trying to find all that out a little bit. But I think what we're finding is that North Americans just use a lot more power. And what we are finding, this is from a different building we did. This one's up in northern BC, but we found that an individual suite uses amazingly different amounts of energy. These are each individual suites, these blue ones, same suites, they're all studio suites. And you see one's up at 135 and one's down at 15. That 15 may be unoccupied or something, but you know, you can see the wild variation in usage in terms of what people actually use. And that red line is kind of where PHPP thought we should be on that particular building. So you can see North America use quite a bit more heat. So then we looked at annual gas consumption. And again, more hot water seems to be used in this building. Now this is a bit of an estimate, so it's not terribly accurate, but based on some data that we got from our electrical or mechanical consultant in terms of water flow and how much was hot water, these are the kind of numbers that we got, that there was quite a bit more gas consumption making hot water. That's all gas is used for in this building than we would have expected, again, from a PHPP. And the monthly electrical energy use in the heights, you can see that it doesn't vary that much winter to summer, if you kind of look at that. And that's because there's just so many fixed loads in a building like this, and we're not using much energy for heat. We're very, very low heating energy in this building. So this is kind of what, I should have had a slide of what this would have looked like for a typical building, but you see the heating is almost non-issue in this building. It's really the gas consumption for the hot water production. That's the biggest piece. And then what people are using in their suites. But we've cut the heating energy way, way down. Now, if we changed to those sand and heat pumps to create our hot water energy, this is what this would look like in terms of percentages. And so this is kind of what's interesting about the building. And we then looked at, okay, how much energy is being used by the gas to make hot water. If we turn it to a heat pump, because they have a much higher COP, gas might be 80, 85, 90% efficient, whereas a heat pump is going to be maybe 2.5 to 4 times as efficient, depending on COP. Depends a little bit on outside air temperature. But even when we did that, it still costs a little bit more under current conditions to run the electricity. Not significant. And as our carbon taxes catch up and as the gas price goes up, this will change quite a bit. And so I think it is the right way to go. We thought we'd compare this building to the total energy use intensity, which is part of the STEP code, the highest level of the STEP code. If we change the gas to heat pump hot water, we would actually be under it. So that was kind of interesting. And this is performance measured. So in fact, the building would have gotten there. So this was this whole thermal comfort problem we were dealing with. And it's just, and humidity again, wasn't too bad, but thermal comfort, we did find that we were getting some overall overheating in those summer months. And this is kind of important to figure out. How do we, we got to think about this moving forward. Particularly, we had that heat bomb that happened last summer. So the other thing you got to remember is you got to change your filters. And it, 40 days. So you can see these filters plug up. Again, this is on a busy street in Vancouver. So maintenance of filters becomes important. But why that's important is when you design a building, if you don't make those filters easy to change, they're not going to get changed. In this case, you open a door, you pull out the filters, you put new filters in, and you're done. But if you got to get up on a ladder and move a ceiling tile and undo a screw to put a filter in, it ain't going to happen. So I think that as a design moving forward, we got to really be thinking about these things as we go. And so this is just this idea of climate change and what's going to happen and how are we going to figure out moving forward how we're going to deal with overheating in our buildings. I don't think heating's our problem anymore, especially in a multi. It is going to be overheating in these multis. We can insulate for our thermal comfort, and we should insulate for our thermal comfort. So anyways, this is kind of where we think we ended up. This is just a couple of slides that were kind of at the end, but these are options for how to deal with overheating, whether you shade your windows properly, whether you put exterior shutters on. There are some grids you can put on, screens you can put on that actually allow you to see through, but actually take care of the thermal or the overheating. This is the building that's under construction about a block away right now. It's at the slab level right now. And on this one, we put exterior blinds on. So and we put some cooling in the supply system. So in this case, we've got 2 bigger units on the roof, and they have a cooling and heating coil in the supply line that then puts the ventilation down into the suites. This is how we've done it. We were going to generate with these big Colmax, but after a cost-saving exercise, we went, We are now using the Sandins, which is what I wanted to use in the first place. The engineers wanted to use these, but again, we're using the CO2-based heat pumps. These are all passive house projects that our office is working on. Some of them are built. This one is finished. This one is finished. This one is almost finished, and maybe we can do a tour. This one is under construction. And this one's, I was just there yesterday. It's on Friday. It's up in northern BC. So all these are projects that we're working on. Anyways, that's the presentation.